Hello and welcome to Sunday's edition of Cracking the Cryptic, and a puzzle that comes recommended to us by some of the greatest solvers and setters in the world of Sudoku. This puzzle is called Addition by Subtraction. It's a lovely looking puzzle. It's by Kane Puzzles, which is the pseudonym of Chan Erturan, the Turkish phenom. I think Chan is still, probably just 17 years old. Has been coming incredibly high up in the World Sudoku Championship for years and years, and it is a quite brilliant mind. And I love this. Look, there's subtraction signs, an addition sign, and thermometers, and that is all. And people who say this puzzle is brilliant include Codec, Mixo, I want to say Pietato, I want to say Foulon Hill. These people are very, very clever. I can tell you actually that Mark had a go at this and had an awful lot of trouble with it. So I think it's hard. It's got 4 stars out of 5 for difficulty on Logic Masters Germany. So I'm looking forward with some trepidation to having a go at it. I have to say, I love Chan's puzzles. I think he's one of these incredibly gifted setters. People like Sam Kappelman-Lyons come to mind. People who are just, they probably don't realise they are, but they're just super, super gifted when it comes to setting puzzles. So I'm sure we're in for a treat. The rules are very short indeed and all standard, and we'll have a go at this in a moment or two's time. Now, I don't have a great deal of news for you today, so I'll give a quick plea to have a look at our competition, which is running over on Patreon. Have I got something where I can show you this? I should have, shouldn't I? Is that going to work? No, that's not going to work. Oh, bobbins. Well, it's Back to the Future. It's a Back to the Future themed Sudoku hunt by the great Blobz. 10 wonderful puzzles. Thousands of you have been having a go at it already. It's phenomenal. It really is phenomenal. Do check it out. The puzzles are great, the theme's great, the whole thing's great, and it's a lot of fun, and you've still got ages if you'd like to be in with a chance to win the competition. It closes on the 20th, and the prize, as usual recently, will be the chance to solve a puzzle with me. So I hope that's some sort of prize. I've been enjoying that mightily over the last few months, and it's resulted in a lot of Sudoku videos, which I think have been really enjoyed in general. So that's the prize anyway, and that's over on Patreon right now, along with all sorts of other extra content. So do join us there. It's our Sudoku club, and it keeps the channel going. Other than that, what else can I tell you about? Actually, I haven't got any birthdays to do today, but we had the most lovely email from Luther in Huron, Ohio, and I thought I might read you some of this because, it was just a delightful thing to read. So, Luther, thank you so much for sending us this email. I'll paraphrase it slightly because I don't like it. I don't want to be very self-serving, but it says. So this is in Luther's words, obviously. I'm a 75-year-old retired man in Ohio. I can't do the accent. I'm unlikely to travel the world, yet I owe a debt of gratitude to 2 men in England. At various times through the years, I've done Sudoku, first by picking up magazines, then later online. The puzzles I found online seemed to be either so simple that with just a little bit of thought I could simply fill in the numbers, or so difficult that I couldn't even figure out where to start without guessing. This was completely unsatisfying. Every once in a while I would do a puzzle here and there, but I can't say that it was something I would look forward to. A couple of years ago I was randomly surfing through YouTube and I came across one of Simon's Sudoku videos. I had no idea that Cryptic Sudoku even existed. I found the videos to be very entertaining, and cracking the Cryptic became a regular part of my day, twice more often than not. Eventually I downloaded the CTC app and started solving for myself. Another epiphany happened when Mark mentioned connections. I wandered off to the New York Times and found a puzzler's paradise. It's important at my age to keep the brain stimulated and working. Cracking the Cryptic has brought me that. Now, I have a regular morning mental exercise routine. I open the Times for strands, mini, Wordle and connections, and occasionally a crossword, the Boston Globe for a line, and finally I open the Cracking the Cryptic app for a puzzle or two. It's immensely satisfying to solve one of these puzzles without a hint, though I don't always manage that. In the afternoon I watch the clock for the times when I know the CTC videos will be available. Watching your videos feels like a visit with a friend. Thank you for being there, and thank you for doing what you're doing. I mean, I talked earlier on in the week, was it Tuesday, about writing thank you notes and what they bring to the person who gets the note. And Luther, I can tell you the amount of pleasure I got from reading your email was tremendous. And I am very, very appreciative that you took the time to send that in. And I mean, actually, it resonates so much with me. I have a daily puzzle routine too. It's a bit like yours. It includes things like all the LinkedIn puzzles, the Times crossword, of course, Nickly puzzles, Cracking the Cryptic puzzles, just loads of puzzles. And I think it does my little brain a modicum of good too. So anyway, there's a little message over the pond from Ohio, and thank you, Luther, for sending it. Now, do I have anything else to tell you? I don't think I do. Let's get on with Chan's puzzle now. Addition by subtraction. These are the rules. We have got normal Sudoku rules applying, so we've got to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. Along thermometers, digits increase from the bulb end. So, look at that cell there. If this was a 2, this cell doesn't have to be 3. It just has to be bigger than 2. So it could be 5. I tried to type 4 then and a 5 popped up, so I said 5. So 2, 5, 7, 9. That would be a completely legitimate way to fill a thermometer. So just as mercury rises as the temperature rises in real life along thermometers, in the Sudoku world, digits rise as we move from the bulb end. Now, each purple line contains a set of non-repeating consecutive digits in any order. There is only one purple line in the puzzle. Oh, I see. Right, so what that's doing is it's making sure we realise that this is a 5-cell line, because otherwise we could have interpreted it, I suppose, as that being a line and that being a separate line. We are not supposed to interpret it like that. And in fact, it might amount to the same thing. But anyway, there's one line in the puzzle. And then there's only... Alright, so let's just understand what that means. So that means if that's a 1, these squares would have to be the digits 2, 3, 4 and 5 in some order, because the digits along the line altogether have to be consecutive. And then adjacent digits on a green line differ by at least 5. So if this was a 1, this square here has to be at least 6. It could be 6, 7, 8 or 9 and be at least 5 different from 1, but it would have to be one of those, because if it was less, say it was 5, these only differ by 4, and that's not good enough. So don't do that, or you'll get the puzzle wrong. That's all the rules. Do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. I'm going to start off by saying something completely fatuous, which is that there must be a 5 on this central cross, because it's 5 consecutive digits, and let's say the digit 1 was on the line somewhere. Well, then the digits are going to be 1, 2, 3, 4, 5, and if the digit 9 is on there, which is the other extreme digit, then the digits on the plus are going to be 9, 8, 7, 6, 5. So 5, it doesn't matter what the composition of the line is, 5 is on it. And then, so, it is symmetrical, is it? Or not quite. I was just going to say, we're seeing a lot of puzzles over the last couple of weeks or so that are highly symmetrical. And this is another one, isn't it? What I mean by that is, let me just quickly draw in a line. If I draw this axis in, I want to imagine that we rotate the grid around this cell sort of 180 degrees. You can see that almost everything would match up. The things that don't match up are these. That is where the symmetry is broken. So what does this mean? Well, it might not mean anything, but what it does suggest is that if we do find some logic in the puzzle, say we found some logic, oh whoopsie, I didn't mean to do that. If we found some logic up here, it's very likely that logic will also have an effect down there, because that is the rotation, that is the reflection, I suppose, or the rotation of this box around the negative diagonal. But I'm not terribly keen on getting involved in these thermometers, I have to say, because, well, that's a 5-cell thermometer. So I think that digit has 5 options. 1, 2, 3, 4, 5. If this is 5, 6, 7, 8, 9, yeah, that's fine. So each cell on this thermometer has 5 different options. So I bet you what's happened here, why Mark's had trouble with this, because Mark's standard way of solving thermometer puzzles is to heavily pencil mark them. So he would have put 1, 2, 3, 4, 5 here, 2, 3, 4, 5, 6 there, etc. And that is just, I think, a recipe for madness, because there's so many numbers then in the grid that you're trying to sort of distill down and make sense of. I mean, the things that I do with thermometers are far more basic. I try and think about the fact that some very basic things. So along a thermometer, if you want to put a 1 on a thermometer, it has to go in the bulb, because this can't be a 1, because that would then be a 0 or a lower, and that doesn't exist. Similarly with 9s, we can only put 9s in those cells. So 9, no, it doesn't matter. 9 in column 3 has to be in one of those cells. It could be something like this, actually. Let's just have a think about this. Where is 9 in columns 3 and 7? Now that's not going to be good enough, because there are 4 options. But if we can find... No, I can't. It's actually a slightly interesting point, is that the same is true for 8 in those columns. Because you can't actually put 8 in this position along a thermometer, because that would be 9 and that would be 10. Same is true here. Same is true here. 8, 9, 10. Now 7 could go here, so we can't quite do the same for 7. In fact, 7 could go there as well. But 8 and 9 are confined. So is it I wonder if it's the same going horizontally. Let me just have a think about horizontally with 1 and 2. Have we got something similar going? Yeah, 1 and 2 can't go there. That's the 3rd cell on a thermometer. They can't go in those. Yes. Okay, so there is something weird going on. There's something weird going on with 1s, 2s, 8s and 9s. Same here. It must be the same because of the symmetry. I have any logic I do that doesn't involve those thermometers is symmetrically applicable. Oh dear. No, I was about to say something that's total and utter gibberish, so... Well, okay. One thing I have learnt, although it's not Fistamafel somehow, is it this? I was going to say, is it set? Which actually would make sense with Mark having trouble with it, because Mark never really likes thinking about set. But that's made me wonder whether Fistamafel's in point. Fistamafel is the theorem, of course, that these 16 cells in any Sudoku, the 16 cells that surround the central 3x3, are the exact same digits as those 16 cells in the corners. No, I don't think it is. I was just wondering... was wondering if it's something to do with 8s, 9s, 1s and 2s, because we've confined them to the Fistomophel ring. Well, we know that the 1 and the 2 in row 3 are there, the 1 and the 2 in row 7 are there, 8 and 9, 8 and 9. So I know that the I know it might be to do with this, you know. So it might be... No. No, I'm not sure, actually. It might not be Fistomophel. And actually, set itself is... What? I'm not actually sure how to even think about set itself. What are we looking at? The sort of the same lattice for thinking about set? I'm not sure. Let me just have a think about that. Oh, okay, yeah, that's going to be it. Right. Ah, right, okay, let me just explain what I'm noticing there. Okay, so I definitely think there's something going on here, so we're going to talk about this. It's actually quite interesting how I've come up with that as an idea. So sort of come up with it by noticing 1s and 2s are restricted in the rows, these two rows, and 8s and 9s in the columns. And that sort of guided me to wondering from a set perspective, and I'll explain what this is in case you've never seen set before. It sort of guided me to what might be the constrained rows and columns. So the way to understand set is to understand that we can highlight column 3 and column 7, and we can absolutely now state what these purple cells contain, because this column is a complete column of the Sudoku, so it will contain the digits 1 to 9, and so will this column. So the purple cells are definitely two sets of the digits 1 to 9. There's definitely 2 1s, 2 2s, 2 3s, 2 4s, all the way through to 2 9s in purple. I don't think any of us could disagree with that. Now, if I highlight row 3 and row 7 in a different colour, what colour? I think I will keep with green. I can say that the green cells also contain 2 1s, 2 2s, 2 3s, 2 4s, etc., etc. Now, in other words, we can say ab initio, before we do anything else, that the set of green digits and the set of purple digits are identical. Now, the thing that we need to get our heads round is what happens if we remove a cell from green and purple that is this one, for example, that's in both of the sets. Now, if I remove that cell from what's in green and what's in purple, what can we say about what remains in green and what remains in purple? And the answer is that what remains in green and what remains in purple must still be the same thing. Because they were the same, we agreed that, and I've taken the same thing out of both. You don't have to know what this digit is. We're not taking the digit out, we're taking the cell out. And we can do the same for this, and this. So we're in this situation where the remaining cells in purple are the exact same digits as the remaining cells in green. Now, why did that catch my eye, and why is that making me think? Well, look, if we look now think about this from a pure thermometer perspective. And what I can see is that all of the green cells seem to be on the ends of thermometers, and all of the purple cells seem to be on the beginning of thermometers. So there must be a mathematical constraint, if you like, on the remaining green and purple cells. Now, what do I mean by that? Well, let's try and work it out. Let's try and work it out. So let's look at this thermometer. Now we can say absolute. I mean, if this thermometer contained 1, 2, 3, 4, these two greens would add up to 7, and these two purples would add up to 3, wouldn't they? So the difference, the minimum difference between the green cells and the purple cells on this thermometer, and therefore I suppose on this thermometer, is 7 minus 3, which is 4. So the minimum difference, if we remove all those, is 8. Now the minimum difference here, if this was 1, 2, it doesn't matter whether it's 1, 2, 3, 4, 5 or 5, 6, 7, 8, 9. I mean 5 and 6 versus 8 and 9 is 11 minus 17 is 6, isn't it? Yeah. Does that make sense? 5, 6, 7, 8, 9, 17, 11, 1, 2, 3. Yeah, it does make sense because the minimum difference between those two cells is 3 and the minimum difference between those two cells is 3. So the minimum difference between those two cells and those two cells is 2 lots of 3, which is 6. Right. So for these two thermometers, it's double 6, which is 12. And for these two thermometers, it's double 4, which is 8. So the 4 corner cells, the 4 thermometers in the corner of the puzzle, we know that the green cells are at least 20 greater than the purple cells. At least. Now, that's not the end of the story though, is it? Because we also know that that cell, if that's a 1, that's a 3. So there's another 2 of difference there and another 2 of difference there. So that's another 4 of difference. So 24 is the minimum difference between by which the green cells on thermometers exceed the purple cells on thermometers. But, so what this matters for is going to be these cells, the ones that aren't on thermometers, because we know the collection of green and the collection of purple overall, they're the same digits, and yet all the thermometer digits are completely biased in the green favour. So that means all of the purple cells that are not on thermometers need to correct that difference. So that what we've now learned is that these four purples are at least, at minimum, 24 bigger than... Hang on, so those ones with a red flash are 24 at least bigger than those greens with a yellow flash. Now, 24 is a lot, actually, because if this is 1, 2, if those were all 1s and 2s, which is the least we can make them, then that adds up to 6. So the minimum value of yellow is 6, which means the absolute minimum value of the red cells is 30. That's the minimum. Now you might be persuaded there to write 6, 7, 8, 9 in there. That's not true though, is it? Because these don't have to be 30. These could be 34. If they were 9, 8, if they were all 9s and 8s, they would each add up to 17. So if these were 9s and 8s, 34 minus 20, these would be 10. Although the difference could be stretched out. So how do we do this then? This must be relevant. It's too interesting for it not to be relevant. Although I'm a little bit worried that I've got carried away by thinking about set here. I'm slightly concerned I've not really understood what this is doing. And I know, what did I know initially? I knew 8s and 9s were in that string and not here. So, and I know 1s and 2s are in this string. So if that was, let's say this cell was a 1 or a 2. You see, hang on, how could both of those be 1 and 2? Then these would be at least 3 and 4, 7, 10. No, that you can do that actually. They could be 1, 2. These could be 3, 4. These could be 1, 2. These would add up to 10. If those, providing those were an 8, 9, 8, 9 pair, that would work. Ah, no. Okay. No. Right, how does it work? Because what we can't do, I've just noticed, you can't do 1, 2, 1, 2 there, and 8, 9, 8, 9 there. Not because of the thermometer logic. The thermometer logic, because we know the minimum difference between yellow and red is 30. No, it's not, it's 24. The minimum difference is 24. But here, the difference is way more than that. We've got 28 as the difference, I think. Let me just double check that. 6 there and 34 there. 28. So the maximum difference we can create is 28. The minimum difference we know exists because of the thermometer logic is 24. So we're looking at either 24, 25, 26, 27 or 28 as a difference. 28 is definitely not possible as a difference because look what's going to happen to the plus sign. You're going to have a 9 on it because where's 9 in the middle row? But in the middle column you're going to have a 1 on it. But 1 and 9 cannot be in a 5-cell sequence of consecutive digits. That does not work. So, hang on. But something... I think there has to be some sort of repeatage between yellow and red. Imagine yellow and red had no repeats. The maximum you could make red is 30 by making it 6, 7, 8, 9. The minimum you could make yellow would be 1, 2, 3, 4, which is 10, and the difference between 30 and 10 is 20. It's not 24. So something's repeating in yellow or red or both. But if something repeats in yellow and in red... No, what do I mean? No, I don't mean that. I mean, if something repeats in yellow and something else repeats in red, those two things cannot be miles apart because they have to be... They could be 4 different. I mean, it could just all I'm thinking is let's make that 1, 2, 3, 4, 5, and let's say that there's a 5 in red and a 1 in yellow. That's possible. But if we instead of that said 6 repeated here, so let's put 6 in those two and make those, I don't know, 8, 9. Now I've got a 6 on here. I can't now repeat a 1 in yellow. So, but I could repeat a 2 in yellow. Oh, I don't know how to do this. This is a bit confusing. I'm getting confused now. Can feel. I don't know. I feel a bit like a thermometer often when I'm solving on camera. I feel like my brain fills up. And at the point it fills up, it can't think properly. But it's got like, providing there's a bit of slack at the top of my brain will work okay. But I'm getting a bit close to the top at the moment. Hang on, I just want to recapitulate. I need to think that through again. I think I better think it out again. I'm reviewing. If there is definitely at least one repeated digit. Because we can't have 6, 7, 8, 9 versus 1, 2, 3, 4. So let's just imagine a digit repeats in yellow, just for the sake of exposition. Let's just imagine a digit repeats in yellow. That gets thrown onto the X. In fact, it gets thrown into one of those three positions. Now, if that's true, if we do repeat a digit in red, that digit cannot be higher than the repeated digit in yellow plus 4, I'm going to say, because I'm looking at my 1, 2, 3, 4, 5 example. So we could have I'm wondering how much of my 24 that uses up. It's not very much, is it? Is it 8? Yeah, let's just look at that example. So imagine you had double 1 here and double 5 here. That's possible. That's totally possible. They're only 4 apart. So they can coexist on this plus sign very comfortably. Well, not very comfortably, just, but they could. So of the 24 that needs to be corrected by red being greater than yellow, this caters for 8 of it maximum. So there's still 16 of difference to be catered for by the difference between hang on, that doesn't work. That doesn't work. You can't do that. You can't do that because let me just explain what I'm thinking there. So what I'm saying is, if there's a digit in yellow that repeats and there's a digit in red that repeats, the problem you've got then is that these two reds have to be 16 bigger than these two yellows. How on earth can you do that? You can't. Because the only way of doing that, actually, and I've done a terrible example here, I'm going to change this. I'm going to make those 2s and those 6s. It's the same effect. I've got a 4 difference here, a 4 difference here, so I still have to cater for a 16 difference between these two reds and these two yellows. And you might say, oh, you could do that. Well, I could. That's the only way. These are 8 different, these are 8 different. But now I'm going to have 9 on here, and I'm going to have 1 on here, and that's not going to work. And that's the only way that that could possibly work, because that... yeah, because I know that there is a repeat. So what I've now learned is I know that there's a repeat either in yellow or in red, but there is not a repeat in both yellow and red, because it's impossible to make the 24 difference work if there is such a repeat. So now either yellow or red has no repeats. So imagine that's red. If red has no repeats, we know it's 30, don't we? That's the most it can be. And that's going to force yellow to be 1s, 2s, because there has to be a 24 difference. Now, how does it work the other way round? Yeah, it's beautiful. So if, on the other hand, there's no repeat in yellow, then these have to be 1, 2, 3, 4, adding up to 10, which means that the minimum value of red is 34, and they're going to be 8, 9. So either yellow is 1, 2, 3, 4, and red is 8, 9, 8, 9, or red is 6, 7, 8, 9, all different, and yellow is 1, 2, 1, 2. And I know this is beautiful. This is going to be beautiful. I haven't worked out why yet, but it's going to be beautiful because now we know that we are dealing with the absolute minimum difference between on all these thermometers. Because the only way I could arrive at a 24 difference is by making that cell and that cell 1, 2, 3 apart. And these two 3 apart. So let's call it a thermometer. It's not a thermometer. Well, it is a thermometer, but it is also a remban. It's a sequence of 5 digits ascending from here to here, ascending in gaps of 1. Same is true here. This is a 1-gapped thermometer. This is a 1-gapped thermometer. This is a 1-gapped thermometer. So it's going to be something like 1, 2, 3, 4, or 6, 7, 8, 9, or 2, 3, 4, 5. And these, if that's a 1, for example, it's going to go 1, 2, 3. If that's a 7, it's going to, well, that's obvious. But if it's a 5, that's going to go 6, 7, because the difference between those two has to be exactly 2. Otherwise, overall, we couldn't deal. This is brilliant, Chan. This is absolute genius. So what does that mean? How do we know whether this is, if this is 1, 2, 1, 2, this is 1, 2, 3, 4, 5. I don't think that. I might be wrong about this, so I'm going to think this through. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9, 8, 9, 6, 7. That doesn't that break the whisper? I'd love it if these tiny whispers are the problem. In fact, I think it's that whisper only that's the problem with that. Right, hang on. I'm going to do it the other way around in my head and find out why that's the case. So if these, on the other hand, if these were 8, 9, 8, 9. This becomes 1, 2, 3, 4. These are 1, 2, 3, 4. Yeah, no, it is. This is just sick. It's absolutely sick. Oh, I've just noticed. I didn't spot this before, and you've all been shouting at me. These green lines aren't symmetrical, are they? Because for that to be symmetrical, it should have been there. Yeah, that's interesting. I just didn't notice that. For some reason, my brain told me they were symmetrical. They're not. And this one is absolutely... This might be the most beautiful... let's just... that's fine. This is... Anyway, that's Mark with the most extraordinary text message about Wordle. Anyway, I've got to get that out of my head now. No, but the reason this might be my favourite green line in the history of Sudoku. Because it's so short, you think it can't do anything. I think it does do something really rather pretty. Okay, so we've worked... Let me show you. So the way this breaks... is if yellow is minimummed. So if these are the 1s, 2s, 1s, 2s. Because if these are 1s, 2s, 1s, 2s, what is the plus containing? And the answer is lots of low thingies. And that means that these cells are lots of high thingies in box 5. And this is a problem. Because remember, in red, what have we got? If yellow has the repeated digits, red has no repeated digits. So it's 6, 7, 8, 9. Now look at this whisper. What do we know about German whispers? We know that the difference between the 2 digits on that green line is at least 5. So what are we proposing to put on it, given that we can't put 6, 7, 8 or 9 on it? There is nothing to put on it. Can't put 5 and 0 on it. There's no high digit possible, so there's no way to fulfill this green line. It just won't work. And it's asymmetrical because we're not going to get the same problem by making this 9898. It's going to have a similar effect. This becomes massive. These all become tiny, although we can't put 1s in those, obviously, because that's the second cells on the thermometers. But we know that these cells now all have to be different. And we're going to get 1, 2, 3, 4 quadruples in columns 4 and 6. But there's no equivalent whispers here to give us an issue. So this could work, and I think it's probably going to work. because the logic has taken us in this direction. Now, yeah, okay, so now I'm going to look at this thermometer and this thermometer, because what we said was that the difference, this is a one-stepping thermometer, so that is a 1, 2 or a 3, that is a 3, whoopsie, that's a 3, 4 or 5, let's be very careful. That is a 1, 2 or 3, that's a 3, 4 or 5. Okay, that didn't work. Oh, bobbins. That digit, look, is a 1, 2, 3 or 4. Because it has to be 5 different at least from 8 or 9. No, that doesn't work, does it? Or... It's probably going to be... Not actually sure what it's going to be. I mean, I can see 9 and... Oh, no, not really 8 so much. 9 is restricted in row 3 and row 7. Because of the 8-9 pairs. And, okay... Because 9, if we look at row 3, for example, where's 9? And the answer is I don't know. But it's either there or there. And the same is true here. So there is an X-swing of 9s in rows. Let's just flash that quickly. What do I mean by an X-swing of 9s? Sorry, I'm just trying to see if this is even in any way relevant. I think it might be, actually. We've got, so in row 3, 9 is in one of the blue cells, and in row 7, 9 is in one of the blue cells. And that's going to create a restriction in the columns. So none of these cells now, let me just highlight them, none of those cells, the black cells, can be 9 now. And the way to understand that, if you find this sort of X-wing pattern, that we found in the blue cells, which was a pattern we found in the rows, remember. The 9s could only go in one of 2 positions in these rows. But the effect of that, it's always important to realise, is on the columns, not the rows. And the way to understand X-wings is to ask a facetious question. How many 9s are there in column 1? Now, hopefully you're going to tell me there's 1 9 in column 1, Simon. That's what the rules of Sudoku tell us. I totally agree. There's going to be 1 9 in this column. And how many 1s are there going to be in column 9? And hopefully you're going to say there's going to be 1 9. So there are 2 9s in these columns. And yet we've just said there are 2 9s in the blue cells. So how many 9s are in the black cells? It can't be any. Otherwise there'd be 3 9s in, or 3 9s or more, in 2 columns of the Sudoku, and that will break the Sudoku. So, none of these black cells are 9. And the other thought I'm having is that, remember these thermometers are one-stepping thermometers. So imagine this one is a 9. 9, 9, 8, 7, 6, 5. And if that's a 9, 9, 8, 7, 6. Ah, no. Yes. Oh, I did. Sorry, here's something I haven't spotted, but I've just spotted it now. Look at this thermometer. That's under massive pressure. There's 1, 2, 3, and 4 looking at the bulb of it. Oh my goodness, right. Look at this cell, 5 or 6. It's got to be. It can't be bigger than 6. It's a 4-cell thermo. If this was 7, 8, 9, this would be a 10. So this thermometer is really restricted. And I suspect that's going to tell us which of those can be 9s. I don't know. I can't quite see that. But let me just think about It's not the same for this one, is it? It's similar. Because I've got 1, 2, 3 and 4 looking at the bulb. That's at least 5. So that's got to be, that can't be higher than 7. Because again, 7, 8, 9 is possible, but nothing more than that. So 5 in column 4 is restricted. One of 2 places. Oh, look at column 5. I've got 7, 8, 9, those and those. Those cells, let me just get rid of the black highlighting for a moment. These cells are a 5, 6, 7, 8, 9 quintuple. So neither of those can be 5. And if neither of those can be 5, these are on the tiny thermos. So now these can't be, those can't be 4s. And these can't be 3s. Oh, this is gorgeous. Now I've got a 1, 2 pair in row 5. I've got a 2, 3 pair. Yeah, I've got a 2, 3 pair in box 5. I've got a 1, 4 pair now in box 5. 2, 3, 4. And I still haven't thought about the fact one of these is a 9. 9, 8, 7, 6, 5. 9, 8, 7, 6, 5. Would make that 6, 7, 8, 9. Oh, I know what it'll be. Yeah, this cell can't be a 7. If this cell's a 7, this is an 8. 7, 8 there kills this square, so that can't be 7. But we have to be a bit careful here, because this thermometer doesn't have to be a one-stepping thermometer. These two thermometers here are under different, they're not part of that original logic, so we can't apply it. I can't say that if this is 6, this is definitely 7, and this is definitely 8. That is not true. It might turn out to be true, but it's not logically forced to be true. Sorry, and what if that one's 9, 9, 8, 7, 6? So if either that is 6, right, yeah, that's fine. Okay, so this cell is known, I think. Yeah, let me try and explain that. It's not actually very easy to see, but one of those is a 9. So one of these is an 8. One of these is a, oopsie, one of those is a 7. One of these is a 6. And possibly this is a 5. But if this is 5, look, this thermometer, if this is a 5, this thermometer goes 6, 7, 8, 9. But if this is a 6, which is the other possibility, this is a 7. So either way, that is always a 7. So that thermometer goes 7, 8, 9. I'm going to just get rid of my pencil marks there because I don't trust myself not to realise that that's a thing. Now this is now not 8. Oh, please do something. This is not 8 or 9. This is not 7. These are not 7. Let's make sure we get rid of the right things. So that's a 5, 6 pair apparently. Okay. So I've now got an 8, 9 pair and a 5. Ah, this is a 7 by Sudoku. I've got a 5, 6 pair here. So that's a 7, that's a 6, that's a 5. And we are slightly off and running again. 5, 6. This square must be an 8 or a 9. I mean, how brilliant do you have to be to set this? I mean, it's ridiculous. Right, look at column 5. Those two squares are a 1, 2 pair. Just by Sudoku in the column. So now in boxes 2 and 8, I've got a 1, 2, 3, 4 quadruple. So that square's a 5 or a 6 by Sudoku. And these squares are 7, 8, 9 by Sudoku. And that is not doing anything, I don't think. Okay, wow. 3. these cells are 3, 4, 5, 6. I might. Do I pencil mark that? 3, 4, 5, 6. No, I don't know actually. Sorry, and if this is obvious to you all, I sincerely apologise. I'm still a bit holiday brainy, I think. I'm not actually feeling like my brain is topped up, like the blood in my brain has reached the top. I think I've reset from that earlier moment. It feels like I'm not a million miles away from seeing how to do this. I just don't see how to do it. Oh, I know what it'll be. I've got it. It's easy. Oh, it's beautiful. I've done it. The blue squares, I can unwind them. How can that be 9? Either this or this has to be 9. If that's 9, 9, 8, 7, 6, it's going to clash here. Because this must be a one-stepping thermometer. So that's 9. That's 9. 8, 7, 6, 5 is how that's going to go. So it goes the same way this way. That's 7 in box thingy, box 2. Right, let's just be really careful here. Yeah, look at this row. Now this square is 1, 2, 3 or 4, and that creates a quadruple here. But we know in box 8, the 3 and the 4 are in these squares, so this square's become a 1 or a 2. I've now got a 1, 2 pair in column 3. I think these are 3, that must be a 3 or a 4, because it can't be a 7. Oh, in fact, where's 7 in the column? It's got to be here. And now, the fact that these are a 3, 4 pair and on a thermometer, I can understand. 3, 4, 5, 6, remember, it's a one-stepping thermometer. So this cell is also 1 or 2. It's sort of the symmetrical, whoopsie, counterpart to this one, isn't it? Where's that digit in this row? It's got to be there. So now, in this column, I need 3, 4, 7 again. And again, the 7 goes in. I should. So 3, 4, 5, 6 is how that thermometer works. Just give me a moment. Now let's see. Can we do? Right, that's not 6. That's not 5. That's not 5. That's not 6. This one? It almost feels now like it's going to have to be maybe this whisper or this whisper that are going to do some damage, because we've done so much. Oh, where's... No, we don't need it. Where's 3 in this box? We can place it. Presumably... Oh, I'm skipping. My spacebar's jumping again. So this square here is 4 or 5. Now, does that logic... Yes, that logic works exactly the same way in box 7. That's 3 by Sudoku. So now this isn't 3. I've got a 4, 5 pair in this row. So I've got a 3, 6 pair now that's fallen out of that. These squares are 1, 2... Actually, that's worth pencil marking. 1, 2, 8, 9. Those can't be 9. Those can't be 8. Okay, no, that didn't work at all. Sorry. What about those squares? 1, 2, 4. 1, 2, 4. Presumably same down here. 1, 2, 4. 6. There we go. There's more things to be done here. So that's interesting. That is a one-stepping thermo. That one isn't. And in this row we haven't put in 1, 2, 8. So this is the only place 8 can go in this row. That's got to be a 1 or a 2. And in this box we haven't put 1, 2 and 9 in, and we can do it. So we must... Why couldn't I do that up there then? That's weird. That feels wrong, doesn't it? It feels almost like I haven't taken advantage of some sort of symmetry trick that's available to me. So how do I... if I can get this resolved, why can't this one be resolved? Oh, well, maybe, okay, so maybe it is just the fact that this, yeah, it's probably that that thermometer got resolved and this one hasn't. It's slightly odd though, isn't it? Slightly concerning. Or, oh, I see. Right, this green line has got to have a high digit on it. If that's a 6, it's got to go there, and that's going to be next to a 1 to be 5 different. If it's a 7, look, it's got to go there, and this is going to be a 1 or a 2. So between those 3 cells now, I've used up 1 and 2 definitely in this box. So these squares can't include 1 or 2, or 8 or 9, so they're from 3, 4, 5, 6, 7. Oh, I was about to say, where's 5 in the box? I was hoping it was going to be there and that would resolve this, but I've realised that could be 5. Bobbins. Okay, let's try. How do we do this then? Sorry. Is it going to be? It might be colouring 9s and 8s. I can see we can colour these against each other. Or one of these thermometers has a 2. One of those is a 2. One of these is 1, 2, 3, isn't it? That might be relevant. Whichever one of these is 1, 2, 3. I'm just thinking, imagine that was 2. That would, no, yeah, if that's 2, that's 1, and that has to be 2. So there would be 2s in both of those positions, and a 2 on that whisper. Do I think that's likely? I think that might be likely, because that would tell us that this had to be 7. You couldn't put 6, 1 on it. So I suspect that's a 2. So maybe we could disprove this being a 2. If this is 2, that's 2. No, that's easier, actually. This would be a 1. Sorry, I can't see how to do this. Well, I can't see at all how to do it. Oh dear. I've nearly pencil marked everything as well. It's probably Sudoku, that means, doesn't it? It probably is Sudoku. That digit is the same as that digit, it's the same as that digit. I'm just going to quickly highlight those for a moment. Can I extend that? That one's so it's the same as that one actually. This one. Oh, that's easy. Why couldn't I do that before? Yeah, sorry. So what I've said there is that this indigo digit is that one in row 7. That seems very clear. Therefore, by Sudoku, it's this digit. That seems very clear. But then in row 5, where's indigo? It seems to have to be there. Because it's not this one. That's already got indigo looking at it. So this is indigo. And now where's indigo in box 3? It's got to be there by Sudoku. So that's definitely not... I've got 4 in the corner. Well, that does that one. So that's 5. That's 4. That's 4. That's... Okay, so that is different from a symmetry perspective, isn't it? We've got a 4 here, but a 4 in the corner in the other place. Yeah, let's quickly give this one a different color. So that, in fact, maybe, you know what I'm going to do? I'm going to get rid of, just going to get rid of my green, my original coloring. Now we don't need this coloring either. We don't need yellow. We don't need red, I don't think. I don't think we need my 9 X-Wing colouring either. So we'll have orange here. Now that's got to be orange. That's got to be orange, so I can get orange. Look, in box 1, which means that is definitely not 9, and now 9 gets placed in box 1. Now that's 9, that's 8, here we go. That's 8, that's 9. That's orange, which we could have got a different way, but I didn't spot it. So now indigo has to be on this, doesn't it? It has to be, because we need a 1 or a 2 on this whisper line. Because its high digit is 6 or 7. Oh, yeah, and where's indigo? Oh, look, the corner digit's an 8. Sorry, I didn't spot that either, but that's true. Now this is definitely indigo, so that's definitely... Oh, this is going to do it. This is beautiful again. Right, because now this digit is a low digit. So it's a 1 or a 2, and it is next to 7. Because that's the only high digit available. This digit can't be 6 and it can't be 8, 9. It needs to be 5 different from 1 or 2. So that's 7. Oh, so maybe that could still be 1 then. Okay, but in the column, what's that digit? 5, I'm going to claim. Just by Sudoku. So that's 5. That's 6. That's a 6, apparently, by Sudoku. So this is 3. So this digit is not 3. Or 1 or 2. It's got all 1 and 2 looking at it. So, oh goodness, my space bar's going crazy. So then 4 goes here. So that's got to be 9 on its whisper. So 9, 8, 8, 9. This 4 sees that. So that's 4, that's 1. Now all I need to do is get one of these to see a colour, you know, either my indigo or orange. What's this digit? That's 3. Yeah, that's done it. That's done it. Because this is 3, that's a 2. We have to colour this. But it can't be orange, because orange has already appeared on its own thermometer. So that's indigo. So indigo is always 2. Which means orange is always 1. And we know, don't we, that the thermometers are stepping them, one-steppers these were. So that's 3, that's 4. That's seeing 3 and 4. So this is just, this is one of the most brilliant puzzles. Honestly, it is just insane how good this is. Now that's orange, so that's orange. 1, 2, 3, 4, 6 and 7. So that's 7, that's 6. I don't know how well I did the Sudoku part of that, but I am reasonably delighted to get through. And finish. I think it must be absolutely stunning. That is absolutely stunning, Chan. That's one of the greats. That is just beautiful. To do that with the addition by subtraction. Hang on. I didn't. Did I? Is that how I did the? It is. It is sort of how I did the puzzle. I sort of had to do some addition and subtraction to make the maths work. That is ridiculous. It's a ridiculous puzzle. I want to colour that in purple just because I do. There we go. That is unbelievable. Fabulous. Absolutely loved it. Absolutely loved it. Let me know in the comments how you got on with that. That is a masterpiece. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.